Hello everyone, I'm Wang from Peking University. It's my great honor to give a presentation here. The topic of my presentation is effects of low-temperature chemical reactions on ignition kernel development and flame propagation in a DME-air mixing layer. Multi-stage heat release is an important feature of large hydrocarbon field due to its complex chemical reaction pathways. As shown in this figure, the three-stage ignition process are dominated by low temperature, intermediate temperature, and high temperature chemical reactions, respectively. Due to the low temperature chemistry, we can observe the well-known NTC phenomenon between ignition delay time and temperature. Furthermore, in some advanced engines, such as the HCCI engines, the low temperature ignition time scale can be comparable to or even shorter than the timescales of the engine combustion process. The formation of low-temperature cool flame has been observed in some diesel spray experiments or in some numerical studies, as shown in these two figures. Therefore, the low-temperature chemistry and the cool flame have been demonstrated to play important roles in engine combustion. In literature, there are two types of configurations that are often studied for the impacts of low-temperature chemistry on ignition process. One is the forced ignition of pre-mixed mixture induced by an external heat source, such as the hot spot or hot particles. It's found that under certain conditions, a cool flame can be directly ignited, which substantially accelerates the subsequent hot flame initiation, leading to a double flame structure. Besides, as shown in the right figure, the cool flame is found to have a wider flammability limit and a lower minimal ignition energy compared to the hot flame. The other configuration that has been widely studied is the auto-ignition in non-premixed mixtures, which is closely related to diesel engine combustion. As shown in the conceptual model, where the right side is cold fuel and the left side is hot oxidizer, the low-temperature ignition is first initiated in fueling region, which is close to the high-temperature oxidizer. Then, a cool flame is initiated and propagates toward the fuel-rich region. Behind the cool flame, the high-temperature ignition is initiated and a hot flame is formed. As a result, multi-branch flame structure can be observed under such conditions, and there are different stabilization mechanisms under different boundary conditions. Apart from the above two ignition configurations, the forced ignition in non-premixed mixture is also a fundamental research topic and has broad applications such as in the direct injection engines or in the relight in gas turbines, where the fuel and oxidizer are not premixed and the inhomogeneous mixture is ignited by a spark or a laser, as shown in the right figure. It has been found that the overall ignition process in non-premixed mixtures consists of multi-phases. Take the Laminar non-premixed jet flame as an example. The phase 1 is the ignition kernel development, involving the generation of a small flame around the spark, and the phase 2 is the triple flame propagation, and finally the phase 3 is the flame stabilization, which implies the long-term stability of flame in the burner. Due to the practical relevance of the forced ignition in non-premixed mixtures, many works have been done on this area, such as the forced ignition in 1D counterflow, 2D counterflow, and even 3D turbulent mixing layer. Generally, it's found that the mixture composition, such as the fuel or oxidizer type, and the mixing layer thickness, the spark parameters, such as the spark size and position, as well as the ignition time and duration, and the flow patterns, such as the strain rate in counterflow and the stochasticity in turbulent flow, would influence the forced non-premixed ignition process considerably. However, despite these works, there is no study on how low-temperature chemistry and cool flames affect the forced ignition of non-premixed mixtures. Based on above discussion, we know that the low-temperature chemistry and cool flame are important for engine combustion modeling. Besides, multi-branch flame structures induced by low-temperature chemistries are observed in the forced ignition in premixed mixture and auto-ignition in non-premixed mixture. Nevertheless, the impacts of low-temperature chemistry on forced ignition in non-premixed mixture have not been studied, and this motivates the present study to investigate how low-temperature chemistry influences the forced ignition in a mixing layer. Specifically, we are going to address the following three questions. First, what are the conditions under which a cool flame can be directly ignited? And second, how is the cool flame transformed into the canonic hot flame? And last, what are the cool flame characteristics in mixing layers? To answer these questions, we conducted a series of two-dimensional numerical simulation for forced ignition in a static DME-air mixing layer with pure DME on the top while air on the bottom. The mixing layer is described by an error function with 2 micrometers mixing layer thickness. The gas in the domain is initially at temperature T0 and pressure P0 to be specified later. The mixing layer is ignited by a hot spot in the center, and the hot spot radius is 0.5 micrometers, and the hot spot temperature TIG is varied. This transient ignition process is simulated using the in-house solver EBI DNS form. It's a compressible reactive flow solver based on the framework of OpenFOAM. Another open source library, Cantera, is coupled to handle the detailed transport and the thermodynamic models. A detailed chemical kinetic model with 39 species and over 100 reactions is used. It includes the low temperature, intermediate temperature, and high temperature chemical reactions. Here we first study the conditions under which a cool flame can be directly ignited. Different initial temperatures and pressures and different hot spot temperature are considered. The temporal evolution of the maximum temperature within the hot domain is plotted. As shown in Figure A, under normal temperature and pressure condition, when the hot spot temperature is 2000 Kelvin, a hot flame is ignited, while when the hot spot temperature is reduced to 1800 Kelvin, there is no flame. So under this condition, only the hot flame can be ignited. However, at elevated temperature and pressure conditions, such as 450 Kelvin and 580 M, different types of flame can be ignited by changing the hot spot temperature. As shown in Figure B, when the hot spot temperature is 1400 Kelvin, a hot flame is ignited. When the hot spot temperature is 1200 Kelvin, a warm flame is ignited as the maximum temperature remains 1300 Kelvin. When the hot spot temperature is further reduced to 1000 or 800 Kelvin, a cool flame is ignited as the maximum temperature is only about 900 Kelvin. The above result suggests that under elevated temperature and pressure conditions, a cool flame or a warm flame can be directly ignited in the DME-air mixing layer when the hot spot temperature is within a certain range. Then we are interested in the case where the hot spot temperature is 800 Kelvin and the cool flame is directly ignited. Figure A shows the evolution of the maximum temperature, the blue line, and the maximum heat release rate, the red line, during a long time. A three-stage ignition process is clearly observed, which is identified by 3 peaks in maximum heat release rate as well as 3 sharp increments in maximum temperature. The cool flame, warm flame, and hot flame are initiated sequentially, and the right figure shows the counters of heat release rate, temperature, and the mass fraction of RO2 and CH2O at 20 microseconds, when the cool flame has reached a quasi-steady state before the initiation of warm flame. The cool flame front is represented by the ISO line of 750 Kelvin temperature, which are the black dashed lines in these counters. It's observed that the cool flame shows a quasi-spherical shape and is located fully above the stoichiometric plane, which is very different from the high-temperature ignition in mixing layers. Besides, it's also observed that the cool flame propagates along the ISO line of the most reactive mixture fraction, that is ZMR equals to 0.3, corresponding to the shortest low-temperature ignition delay time. This is also demonstrated by Figure B, where for the cool flame, the mixture fraction corresponding to the maximum displacement speed Zfmax is approximately a constant at about 0.3. We now focus on the transition among cool, warm, and hot flames. This slide shows the details about the initiation of warm flame. The counters of heated release rate, temperature, and the mass fraction of H2O2 are presented at two instants when the warm flame is first initiated and fully developed respectively. It can be seen that the warm flame is first initiated at the center of the burnt product of cool flame, where the temperature and the H2O2 concentration is maximum. At 30 microseconds, a quasi-spherical warm flame is fully initiated and it propagates outwardly, leading to a double flame structure of both warm and cool flame. Then the initiation of hot flame is presented. The counters of heated release rate, temperature, and the mass fraction of CO2 are plotted. It's observed that the hot flame is ignited immediately at the intersection between the warm flame front and the stoichiometric plane. Then, a typical triple flame structure is formed. A large amount of CO2 is produced by the diffusion flame branch, where the maximum temperature is about 2400 Kelvin. The hot triple flame propagates along the stoichiometric plane. The rich premixed hot flame branch catches up and merges with the leading warm and cool flame. However, the cool and warm flame are only partially merged by the rich premixed hot flame branch, leading to a pentabranchial flame structure, which is reported for the first. After knowing the transient ignition process, we further conducted a parametric study on this process. First, we changed the mixing layer thickness. The thinner mixing layer, the higher dissipation rate. As shown in this figure, the cool flame ignition time is not sensitive to the mixing layer thickness, as the cool flame is directly ignited by the hot spot and thus is not sensitive to the dissipation rate. As contrast, the warm flame and hot flame ignition is very sensitive to the mixing layer thickness, as they are auto-ignition processes which are sensitive to the dissipation rate. Then we study the impacts of the hotspot size and position. For example, when the hotspot radius is decreased from 0.5 to 0.25 micrometers, only the cool flame can be ignited. When the hotspot is moved up, no flame can be ignited, while when the hotspot is moved down, only the hot flame can be ignited. Overall, different ignition modes are achieved via changing the temperature, size, and position of the hotspot. The underlying mechanism is explained in our manual. Last, we focus on the cool flame dynamics in mixing layer by analyzing the cool flame displacement speed. The displacement speed can be first decomposed into two components corresponding to the contribution from reaction and the thermal diffusion. Figure A shows the distribution of these two components along the cool flame front. It can be seen that the diffusion term is opposite in sign but comparable in magnitude with the reaction term, which indicates that this is a self-sustained flame front. Then the diffusion term is further decomposed into two components corresponding to the normal diffusion and the tangential diffusion respectively. Figure B shows their distribution and comparison. The ratio is larger than 0.3 and thus the tangential diffusion cannot be neglected, which means the cool flame observed here is a partial premixed flame and cannot be characterized by a single premixed or non-premixed flamelet. Overall, the cool flame observed in the mixing layer is a self-sustained partially premixed flame. This slide further shows the dependence of density-weighted cool flame displacement speed on-stretch rate. A very good linear relationship is observed under various conditions. The unstretched cool flame displacement speed is not sensitive to the pressure but is sensitive to the temperature. As contrast, the Mach number, that is the slope of the fitting lines, is sensitive to both pressure and temperature. To summarize, in present study, the first ignition by a hotspot in quiescent DME-air mixing layers is studied. It's found that under elevated temperature and pressure conditions, a cool flame or a warm flame can be directly ignited depending on the hotspot temperature. At relatively low hotspot temperature, three-stage ignition process is observed and cool, warm, and hot flames are initiated sequentially, leading to a pentabranchial flame structure, which is reported for the first time. And we also found that the cool flame in mixing layer is a self-sustained, partially premixed flame. Its density-weighted displacement speed changes linearly with the flame stretch. In future work, we will consider different large molecular fields to investigate the generality of present result, and we will also consider more complex flow configuration, such as the counterflow or the turbulent mixing layers. We believe that this would be very interesting. Thank you for your listening. Please contact me via email if you have any questions.